What's up? What's up? Hi, students. Now, check out these photos. Sometimes that's like you, right? You can't decide what to wear. There's a lot of options, right? What top, what bottom, what movie show to watch, what TV show to watch, right? It's confusing. But these are compound events and these are sample spaces. We will try to organize all the possible choices and there's a probability that you need to solve, okay? Are you ready? That's the lesson for today. All right, so let's start with definitions. Let's start with sample space. Sample space is a set of all possible outcomes. It's a space, literally a space, where you write down possible combinations or outcomes, right? A tree diagram looks like a tree, right? A tree with branches and roots, right? Look at that. It is an organized way for you to list down all the possible outcomes. And compound events is not simply one simple event, but two or more simple events. You're just probably throwing a die or even spinning a spinner, or not just once, but two or more events. Today we will study three tools that will help us organize our sample space. The first one is simply writing down everything. Sometimes they call sample space as simply listing down. Okay, for example, this is the menu of a restaurant. You're required to choose one main dish and one side dish. You have to list down all the possible menus that you can order. So suppose I listed down everything: grilled chicken and salad, grilled chicken vegetable, grilled chicken and rice, baked chicken and salad, baked chicken and vegetable, baked chicken and rice. Did I miss out anything? Look at the combinations. Did I use all of it? Yes, I did. Now, how many possible outcomes are the results? What possible orders could I have? One, two, three, four, five, six. Because I listed down, I can now say there are six. Now, I need the probability of baked chicken, chicken, and vegetable. Baked chicken and vegetable. So, I look at my sample space here, baked chicken and vegetable. There's only one. So I write a probability. So how do I write that? 1 over 6. So you could say less likely, a customer will order that. Now this is a quick check regarding the sample space. Let's read the problem. A bicycle comes in three models: Super, Mega, Ultra, and three colors: black, red, and orange. Construct a sample space to find how many bicycle choices you have and count it. How many possible outcomes? And B, what is the probability that somebody would order a mega bike? So what do? I list down. I could buy a super in black. Let's exhaust all the super. Super in red, super in orange. We're done with all the super. Let's now move on to the mega. Mega black, mega red, mega orange. Then the ultra model. Ultra could be black, ultra red, and ultra orange. Okay, so guys, this is now the sample space. Okay, whenever I wrote all of this is called the sample space. Now, how many outcomes are there? We could easily say there are 9. The next question is, how many would be the probability of getting a mega? These are all the mega. Okay, so I write 3. 3 goes there. And where did I get the denominator of 9? From there. And the simplest form is 1 out of 3. Probability is 1 out of 3, so you could say that's less likely somebody will order that. The second tool is using a tree diagram. Okay, so how do I do that? You roll a standard number cube, a die, and then toss a coin. The number cube and the coin. List the possible outcomes. We want to have a sample space here, but we cannot do that yet. I want to organize it using like branches and roots, right? So what are the possible results of outcomes for a cube? So we know it's 1, 2, 3, 4, 5, 6. And for a coin, it will be what? A head or a tail. But when I throw a number cube, it could be a 1 followed by a head. So I write 1H, right? So, but the first one could be 2 followed by the H. It could be 3 followed by head, 4 followed by head. Let's exhaust listing down all of the one with the head result. And then for a tail, it could be 1 followed by a tail, 2 followed by a tail, 3 followed by a tail, and 4T, 5T, 6T. Okay? How many possible outcomes? We simply add them all. A total of, yes, 12. Okay, but there's a question here. What's the probability of getting a 4T or a 5T? Where is the 4T? Let's highlight it. 4T is over here and 5T is over there. So there are 2. So what do I write? 2 over 12. Or the lowest terms is 1/6. So 1/6 is the probability. Let's have a quick check. You can choose blue or khaki pants. A khaki is like somewhat brown. And a red, yellow, or green shirt. Construct a sample space using the tree diagram. How many outfits are possible? Remember, the pants could be blue or khaki. The shirt could be red, yellow, or green. Okay, make lines so that you won't miss any. It could be what? Blue followed by red. Let's list them down. Blue followed by yellow, blue followed by green, khaki red, khaki yellow, khaki green. So we've listed down everything. How many possible outcomes? We counted it. That's how many? 6. And how many are the blue ones? 1, 2, 3. There are 3 possible blues. So what do I write? 3 out of 6. Lowest terms is 1/2. Okay? The third tool is using the counting principle. Don't be scared. This will make your life easier. There are m ways in making one choice and n ways in making a second choice. Okay? So 2 events. What will you do? There are m times n ways to make the first choice followed by the second choice. In short, it's telling you, yo, just multiply them. Say it again. Just multiply them. Okay, for example, you choose one item from each category in the menu. How many desserts can you order? You need to order one from each. So what are all the possible orders that you could have? Let's see now. Flavors, 5 choices. Toppings, 3 choices. And cone, 2 choices. The rule says just multiply them. So that's going to be flavors times toppings times cone. And how many flavors, toppings, and cones? 5 times 3 times 2, that's 15 times 2, that's 30. So our answer here is 30. Got it? Now let's have a quick check. In the menu, okay, same menu. Cherry Ripple ice cream as a flavor and fudge as toppings were added. So there should be a new number of different desserts. No need to list them. Okay, let's see what we're going to do. Number 1, the flavor before was 5, 3, and 2. But remember, we added one flavor and one fudge topping. So what is our new numbers now? Because we added one, you're now a 6. The toppings is now a 4. The cone is still 2. And the counting principle means what? Simply multiply them. I don't need to list down. I just want to know the total. So 6 times 4 is 24 times 2 is 48. There you go. Now, this example will require us to use all the methods. Let's read the problem. Each lunch for a school field trip has a turkey, roast beef, or bologna sandwich, an orange or apple for a fruit, and a cookie or muffin for dessert. Amanda and Zach would like to know the number of possible lunch options. B, probability of having any meal with no cookie. We're going to use all of the methods. Okay, let's start with a tree diagram. So, first of all, let's start with a sandwich. Sandwich could be a turkey, roast beef, or bologna. Okay, sandwich could be turkey, roast beef, or bologna. And then for a fruit, it could be orange or apple. Take note, I'm just using the first letter. It makes your life easier. So, orange or apple, roast beef followed by orange or apple, bologna followed by orange or apple. Next, for a dessert, I'm required to get a dessert. That could be a cookie or a muffin. So turkey, orange, followed by a cookie or muffin. Turkey, apple, followed by a cookie or muffin. So let's just put that on each of these uh, tree so that the tree diagram could show like a sample space. Okay, so that's the final results. Then the next question is the possible lunch options. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 possible. Okay, or you could use the counting principle. Sandwiches, there are 3. For fruit, there are 2. And for desserts, there are 2. Simply multiply them. You will again get the 12. Okay, so we did counting principle. We did tree diagram. We used the sample space. Oh, this is the tree diagram. A sample space would look like this. So we list down all the combinations. How do I read that? Turkey, orange, cookie, right? Or it could be turkey, orange, and muffin. Turkey, apple, cookie, turkey, apple, muffin. So let's list them down. All the ones that starts with the turkey is TOC, TOM. Okay, followed by TAC, TAM. All of this is with turkey. Now let's go with the roast beef. ROC, ROM, RAC, and RAM. Ooh, I like RAM. That's my best combination. Next could be a B, bologna. BOC, BOM, BAC, or BAM. So how many? Again, that's 12. So tree diagram, it's now a sample space. Now, like we can answer letter B. Letter B. Probability of a meal with no cookie. Look at this. I will circle the meals without a cookie. So you don't have a cookie. You don't have it. You have a muffin. You did not order the cookie. All right. So how many is that? There are 3. So what do I write? I put 3 on top. And what's the denominator? 12. Or the lowest terms is 1/4. So less likely it will they will order a meal without a cookie. You can choose from a model plane, car, or boat. Each model comes in 3 colors, red, white, or blue. A, how many choices do you have? B, what is the probability that your choice is not white? Okay, so remember, it could be a plane, car, or boat. Okay, so what do I write? It could be a plane, a car, or a boat. Okay, and the colors are red, white, and blue, followed by red, white, or blue. Okay, a car red, car white, car blue. Okay, a boat red, a boat white, and a boat blue. Okay, so that's it. How many choices do you have? That's easy. Look at the final choices. We have 3 plus 3 plus 3. That's a total. Letter A. Letter A, our answer is, we could do 3 times 3, which is 9. Okay, now letter B, probability of not white. Not white. Okay, look at the combinations. I can choose plain red and plain blue. Not the white. Car red and car blue. 2. Both red and both blue. So how many? 2 plus 2 plus 2, a total of 6. So that's going to be 6 out of how many total? 9 possible, because I didn't choose those with whites. So that's going to be lowest terms 2 out of 3. So that is more likely. Greater than half, more likely. Use your counting principle. Okay, no need to list them down. To find the number of outcomes are there. Tossing a coin 3 times. Okay? 3 times. Coin 1, coin 2, coin 3. So if you toss a coin, there are heads and tail, 2. The second one, heads and tail, heads and tail. Multiply them. Counting principle is multiply, so there are 8 possible. Okay? A theater shows 8 movies at 3 prices 5 times each day. Oh, okay. 8 movies, 3 prices 5 times each day. How many types of ticket does the theater sell? Okay, simply multiply them. So this is going to be 24 times 5 is 120. See? Counting principle, I didn't need to list them down, no tree diagram, I just multiplied. Now, below is a tree diagram of the possible menu order in a deli. What is the possibility of a customer choosing wheat bread, any meat, and cheddar cheese? So that's what, oh, the total. Let's count the total first. There are how many? At the end, white bread, ham, cheddar, that this counts as one. Look at this. If you count it that way, that counts as one, right? That's how you read all the combinations. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 is the possible combination. You can see it here. Or how else did I know that it's 12? You could multiply 2 times 3 is also 12. So we're good with letter A. Letter B, what is the probability of wheat bread? Look at the choices. These are all the wheat bread and any meat and cheddar cheese. Wheat, any meat, and cheddar. That's one. Wheat, what else? Here, wheat, turkey, and cheddar. That's two. And what else? Wheat, chicken, and cheddar. Okay, look at that. I have three. So for the second question, there are three possible orders. Out of 12, you can simplify that to 1/4. So 1 out of 4, that's less likely. You could say less likely. All right. Okay, let's try this problem. A cube is numbered 1 through 6. If the cube is rolled twice, how many possible outcomes will have two even numbers? Okay, so if I throw the first dice, it could be 1, and the second dice followed by 1, right? I'm doing sample space. 1 followed by 2, right? 1 followed by 3, 1 followed by 4, 1 followed by 5, and 1 followed by 6. Are we good with that? But the first one could be 2. 2, right? The first one could be 2. 2 followed by 1, 2 followed by 2, 2 followed by 3, 2 followed by 4, 2 followed by 5, 2 followed by 6. Okay, we can already see a pattern, right? And then I will have a series of 3. I'll have the series for 4 on the first one, 5 on the first one, and 6 on the first one. Okay, I'll have a total of how many? But I don't need the overall total. Look at this. Two even numbers. If you want to know the outcome, it's going to be how many? 6 for you, 6 for you, 6, 6, 6, 6, 6 times 6, 36. Okay? You might be tempted to choose that. No. Why? Because you're being asked, we want the even numbers. So, starting with a 1, I cannot find the even numbers. These are the even numbers. 2 and 2, 2 and 4, 2 and 6. Where else do you think will I see that combination? 4 and 2, 4 and 4, 4 and 6, right? Forget here, you won't get anything from there because it has to be an even. You could get 6 and 2, 6 and 4, and 6 and 6. So how many yellow circles have I made? 9. So that's the correct answer. Byron bought a keyless entry door lock that has the digits 0 through 9 on the keypad. This one. He wants to choose a 3-digit entry code. How many different combinations are possible if the digits can be repeated? Okay, so this is the lock, right? So we need 3 numbers. Okay, the first number could be, how many numbers can we see here? Obviously, there's 9, but there's a 0 that makes it 10. So there are 10 possible choices. For the second, since it can be repeated, there could be 10 again. For the third digit, there could be 10 again. So use your counting principle. 10 times 10 times 10 is 1,000. A jar contains one blue tile, green tile, one red tile, and one yellow tile. If a tile is chosen at random and then placed back on the jar, and then a second tile is chosen at random, How many possible outcomes contain at least one red tile? Okay, so let's analyze the problem. So let's write the colors blue, green, red, yellow. So the first pick could be a blue followed by a green followed by the first one could be a red or a yellow. Okay, but after picking a blue, it could be followed also by a blue, green, red, yellow, right? First and the second. But if your first is red, your second could also be blue, could be a green, a red, or a yellow. If you chose a green, it could be followed by a blue, green, red, yellow. If you start with a yellow, the second one could be blue, green, red, and yellow. If you want the total outcomes, you could do 4 times 4, which is 16, but 16 is not what's being asked. Check it out. Which one contains at least one red tile? At least one red or two reds. So we need to circle them. Okay, which one here? Blue followed by a red contains a red. That's one. Red followed by a blue, that has one red. Red followed by green has a red. Red and red is allowed because it has at least. It could be more. Red followed by yellow. Okay, is there a green followed by, yes, I need you red. Yellow followed by red. There you go. So I have one. I have four for you. I have one and one. Add them up. 4 plus 1 is 7. All right. Keisha has a bag that contains one red marble, one yellow, one green, and one orange. She makes a table to show the different ways that she can choose two marbles. The first choosing the one marble, replacing it, and then choosing another marble. These are the results. Okay? So let's see. What is missing from the table? So the first one could be what? The first one could be red followed by red, yellow followed by red, green followed by red, orange followed by red. Oh, let's look at the rows. Red followed by red followed by yellow, red followed by green, red followed by orange. All of these are the yellow. So yellow followed by red, yellow again. This is the missing one. See that? Okay, so that's it, guys. Remember, results is equal to action plus your motivation to learn. Okay, good luck in your practice.